43 years ago, a typhoon in the Pacific dropped its central pressure 100 hectopascals in a single day. Nobody has come closer than 3 hectopascals since. It is still the fastest any storm on Earth has ever been measured intensifying. Yesterday, in the same ocean, a storm called Dolphin went from a disorganized mass of thunderstorms to a typhoon with a pinhole eye in 5 hours, and the forecast for it jumped to the top of the scale we use to measure these things from space. Water above 29 degrees Celsius, no shear, nothing in its path. But the structure that makes a storm capable of a record is also the most fragile thing a storm can build, and one ocean away, a day earlier, another storm proved exactly that. If you want to know how this ends, hit the like button and subscribe to the Sky Lab. Drop a comment telling me where you're watching from, and whether you have ever been through a storm that got worse faster than anyone said it would. Now, let's get into it. Part 1. 5 hours over open water. Over roughly 5 hours on the morning of July 28, 2026, a disorganized clump of thunderstorms sitting in the middle of the western Pacific Ocean turned itself into a typhoon with a pinhole eye. Not over 5 days. 5 hours. In the time it takes to fly from Los Angeles to Honolulu, a storm that satellite analysts had been describing as messy and poorly organized became one of the most dangerous shapes in all of meteorology, and the official forecast for it jumped by an amount that would have looked like a typographical error a week earlier. The storm is called Dolphin. Officially it is Tropical Cyclone 12W, and until the early hours of that Tuesday it was doing nothing that would have earned it a second look from anyone outside the forecast offices that track the Western Pacific for a living. I want to give you the number that this entire story is measured against right now, at the start, because everything that follows only means something once you have it. In September of 1983, in this same ocean, a storm called Forrest dropped its central pressure from 976 hectopascals to 876 hectopascals in a little over 23 hours, 100 hectopascals in a single day. That is the World Meteorological Organization recognized record for the fastest intensification of a tropical cyclone anywhere on Earth, and it has stood unbroken for 43 years. That is the bar. That is what the last time a storm intensified this fast actually points at, and it is a real number with a real storm attached to it, not a figure of speech. Now here is what Dolphin did. As of the last advisory before the burst began, the system was located roughly 600 miles southeast of Wake Island, crawling west at about 10 miles per hour, with maximum sustained winds near 70 miles per hour and gusts to 85. A strong tropical storm. Unremarkable. The kind of system the Western Pacific produces 24 times a year without anyone in the wider world noticing. By early on July 28th, it had been upgraded to typhoon status, with sustained winds of 120 kilometers per hour and a central pressure of 980 hectopascals, sitting roughly 4,000 kilometers east-southeast of Tokyo. And then, within hours of that upgrade, the satellite imagery stopped matching the advisory. The cloud shield over the core contracted into something extremely compact. Deep cold convection wrapped itself completely around the center, with almost uniform symmetry, the way a hand closes around a fist, and at the middle of that ring, a very small warm spot appeared on infrared imagery, the unmistakable signature of a clearing eye, with air sinking and warming inside it, while the pressure at the surface fell away beneath. The forecast responded the way forecasts do when the underlying storm has stopped behaving predictably. Guidance carried the system to 145 knots at 72 hours, which is itself a rare forecast to issue. Discussions raised the possibility of the storm reaching a satellite intensity estimate of T8.0, roughly 170 knots, which is effectively the top of the scale forecasters use. Public forecasts projected an explosive peak near 170 miles per hour of sustained wind late on Thursday, July 30th, as the storm passes about 230 miles southwest of Wake Island. If that happens, Dolphin becomes the Western Pacific's third super typhoon of the summer. It is worth pausing on what 170 miles per hour of sustained wind actually is, because the number has been said so many times in so many hurricane broadcasts that it has stopped meaning anything. The force the wind exerts on a structure does not scale with wind speed. It scales roughly with the square of wind speed. So a storm at 170 miles per hour is not twice as destructive as a storm at 85. It is closer to 4 times. Every doubling of wind speed quadruples the pressure being applied to every wall, every roof, every window, every tree, every power pole in its path. That relationship is the reason the difference between a strong Category 3 and a Category 5 is not a matter of degree. Here is the part that makes this worth 2 hours of your time rather than the headline you scroll past. There is no coastline in the way. There is no evacuation order. There is no landfall in the forecast. Dolphin is intensifying over thousands of miles of open ocean with essentially nothing to hit. And that is precisely what makes it the cleanest possible view of the one problem that tropical meteorology has not solved. Over the last 4 decades, forecasting where a hurricane or a typhoon will go has improved dramatically. A 5-day track forecast today is roughly as accurate as a 3-day forecast was a generation ago, and that improvement has saved an enormous number of lives, because it is the thing evacuation orders are built on. But forecasting how strong a storm will be when it gets there has improved far more slowly. And the specific place where intensity forecasting still fails, over and over, is exactly the case Dolphin is demonstrating right now. The storm that strengthens far faster than anyone predicted. So this is not really a story about a typhoon. It is a story about a rate. About how quickly a storm can take heat out of an ocean and turn it into wind. What physical arrangement allows it to happen. What the actual record for that conversion is, and why a storm doing this in the summer of 2026 over this particular ocean is not a coincidence. Over the next stretch we are going to take this apart properly. We are going to look at what a pinhole eye actually is, and why forecasters treat the sight of one as a warning rather than a curiosity. We are going to go back to 1983 and meet the storm that holds the record. A storm that almost nobody remembers, despite having set the same benchmark 3 separate times. We are going to go under the surface of the ocean, because the temperature of the water is not the number that matters, and I want to show you the one that does. And we are going to look at another storm, in a completely different ocean, that did the same thing Dolphin is doing exactly 24 hours earlier, reached the top of the scale and then broke itself. That last one matters more than anything else, and I will tell you why now, so you know what you're watching for. The structure that is making Dolphin's forecast so aggressive, that tiny, perfect, contracted eye, is also the single most fragile structure a storm can have. The thing that makes the 170 mph forecast physically plausible is the same thing most likely to stop it from happening. There is one question sitting underneath all of this that I've not answered yet, because it is genuinely the hard one. Forecasters knew the environment around Dolphin was favourable. They said so. The water was warm, the shear was low, the air was moist. Every box that can be checked was checked. But dozens of storms a year check every one of those boxes and go on to do absolutely nothing remarkable at all. So what happened in those 5 hours? What did this particular storm find? In an ocean full of storms sitting in identical conditions that let it convert heat into wind at a rate that put it in the same conversation as a 43-year-old record. Nothing in the forecast the day before said it would take 5 hours instead of 2 days. Part 2. The storm nobody was watching. To understand what changed, you have to understand how ordinary this storm was first. Tropical depression. 12W came together over the open central western Pacific on or about July 26, 2026. It was one of several systems being tracked in a basin that produces more tropical cyclones than any other on the planet, and there was nothing in its early structure to suggest it would end up in a conversation about records. On July 27th, it was upgraded to a tropical storm and given a name. In the Western Pacific, storm names are contributed by the countries and territories that sit in the path of these systems, rotating through a shared list, and Dolphin is one of Hong Kong's contributions to that list. It is a mundane administrative detail, and I mention it only because that name is now permanently attached to whatever this storm ends up doing, and to whatever number ends up next to it in the record. For its first day and a half of existence, Dolphin looked like what a mediocre tropical storm looks like from orbit. Thunderstorms would flare up near the centre and then collapse. The circulation would drift out from underneath the convection, or the convection would blow off to one side. Nothing wrapped, nothing held. That flaring and collapsing has a rhythm to it, and it is one of the more counterintuitive things about tropical storms. Convection near the centre of a tropical cyclone tends to be strongest overnight and in the pre-dawn hours, and weakest in the middle of the afternoon. It runs backwards from what most people expect, because the daytime heating that drives thunderstorms over land is not the dominant process out here. Over the ocean, what matters more is how much the cloud tops can radiate heat away to space at night, which destabilizes the column from above. So a storm that keeps its convection blazing through the afternoon when it should be sagging is telling you something has changed. When forecasters look at a system like this and ask whether it is about to do something, they are running through a checklist that has been refined over decades. How warm is the sea surface? How deep does that warm water go? How much vertical wind shear is there between the lower atmosphere and the upper atmosphere? How moist is the air in the middle levels, where dry intrusions can kill a storm from the inside? Is there good outflow at the top, venting exhaust away so the chimney can keep drawing? And critically, are the low-level circulation centre and the mid-level circulation centre stacked on top of each other, or are they offset? That last item on the list deserves a sentence of its own, because it is the one that most often decides a storm's fate, and it is the least intuitive. A tropical cyclone is not a flat spiral. It is a vertical column, and it only works as an engine if that column stands up straight. The circulation near the sea surface, where the storm collects its heat and moisture, has to sit directly beneath the circulation 5 or 6 miles up, where the heat is being released. When the two are offset, when the storm is leaning, the warm core cannot form over the surface low, the pressure cannot fall efficiently, and the whole arrangement bleeds energy sideways instead of concentrating it. Half the tropical systems that fail because they never manage to stand up. Outflow is the other one people underrate. A tropical cyclone is a chimney, and a chimney only draws if the smoke can get out at the top. Air rising through the eye wall has to be evacuated outward at the top of the troposphere, 10 to 12 miles up, and spread away from the storm. If that upper-level exhaust is blocked, air backs up over the core, the ascent slows, and the surface pressure stops falling no matter how warm the water underneath is. Good outflow shows up on satellite as cirrus streaming away from the centre in long curved bands, and it is one of the first things a forecaster looks for when trying to decide whether a storm is about to accelerate. Dolphin's readings against that checklist by the 28th were close to perfect. Sea surface temperatures beneath and ahead of the storm above 29 degrees Celsius. Vertical wind shear low. No dry air being drawn into the core. Good outflow. A circulation that had finally stacked itself vertically. Every box checked. And here is the thing that I need you to hold on to for the rest of this video, because it is the hinge the entire story turns on. That checklist does not predict what Dolphin did. Not even close. Every single tropical season, in this basin and in every other, dozens of storms sit in environments that check every box on that list, and then proceed to strengthen at a completely ordinary rate. Some of them never become typhoons at all. The environment is a permission slip. It tells you that something extraordinary is allowed to happen. It does not tell you that it will, and it certainly does not tell you when. Let me give you the yardstick that forecasters actually use for this, because the phrase rapid intensification gets thrown around loosely, and it has a precise definition. Rapid intensification means an increase in maximum sustained winds of at least 30 knots, about 35 miles per hour, within a 24-hour period. That is the operational threshold, and it comes from work by Kaplan and Demaria that has been the standard reference for decades. There is also an informal category above it, sometimes called extreme rapid intensification, used for storms gaining roughly 50 knots or more in the same window. That is the top few percent of everything the atmosphere produces. Think about what 30 knots in 24 hours actually describes as a physical event. A storm sitting at 70 miles per hour in the morning is a serious tropical storm, the kind that closes ports and cancels flights. The same storm one day later, having done nothing more than clear the operational rapid intensification threshold, is a Category 1 hurricane with a defined eye. And a storm crossing the extreme threshold, 50 knots or more, can start a day as a tropical storm and end it as a major hurricane capable of destroying the buildings it passes over. The atmosphere does not usually have that gear. When it finds it, everything downstream of the storm is planning against a forecast that is already obsolete. Most tropical cyclones never do this at all, not once, in their entire lifetimes. Rapid intensification is not the normal way a storm gets strong. The normal way is slow, uneven, interrupted by dry air and shear, and the storm's own mess, taking days to gain what a rapid intensifier gains between dinner and breakfast. So the question this whole story hangs on is not whether Dolphin had good conditions. It did. The question is why this storm, out of the dozens sitting in comparable conditions across the tropics that week, was the one that went vertical. Sometime in the pre-dawn hours of July 28th, Dolphin stopped behaving like the dozens. There is a moment in the satellite loop, and forecasters who watch this basin for a living describe the rate of organisation afterward as extraordinary, even by Western Pacific standards, where the storm simply stops looking like a tropical storm and starts looking like something else. The convection stops flaring and collapsing and instead locks into a solid ring. The centre stops wandering. The whole system contracts the way a crowd tightens around something happening in the middle of it. 5 hours later, there was a hole in the middle of it. Part 3. The warm dot at the centre. An infrared satellite image is not a photograph. It is a temperature map. That distinction matters enormously for what happens next. Because everything forecasters concluded about Dolphin on July 28th, they concluded from temperature. The satellite is measuring how much infrared radiation is coming up from each point beneath it, and converting that to a temperature. Cold means high cloud tops, reaching up toward the top of the troposphere where the air is 60 or 70 degrees below 0 Celsius or colder. Warm means low or clear. So when I tell you that a warm spot appeared in the middle of Dolphin's cloud shield, understand that nobody was looking down a hole and seeing the ocean. They were looking at a temperature anomaly and reading a structure from it. Start with what was there before the warm spot. A developing tropical cyclone builds what forecasters call a central dense overcast, a shield of high cirrus cloud blowing off the tops of the thunderstorms in the core, spreading outward and covering the centre completely. It is the visible exhaust of the engine underneath, and the shape of that shield tells you a great deal about the engine you cannot see. A sprawling, ragged, lopsided, central dense overcast means a circulation that is disorganized, tilted, or being pushed around by shear. A compact, round, symmetric one means a circulation that has consolidated into something tight and vertical. Dolphins went from the first kind to the second kind in a matter of hours. Analysts watching it described the central dense overcast as extremely compact, and the convection as having wrapped completely around the core with uniform symmetry, with what they called frigidly cold cloud tops. That word, symmetry, is going to keep coming up, and it is one of the most important words in this entire story. Then the warm dot appeared. Here is the physics of that dot, and it is worth getting right because it is the visible symptom of everything happening underneath. Inside the eye of a tropical cyclone, air is not rising, it is sinking. The eye-wall thunderstorms surrounding it are carrying enormous quantities of air upward, and some of that air at the top turns inward and descends into the centre. As it descends, it is compressed by the increasing pressure of the atmosphere around it, and compression heats a gas. That is the same principle that makes a bicycle pump warm. So the eye is a column of sinking, warming, drying air. On an infrared image, that column shows up as a small warm patch surrounded by a ring of extremely cold cloud tops. The greater the contrast between that warm centre and the cold ring, the deeper and better organised the eye and the stronger the storm underneath. What Dolphin showed on July 28th was a very small warm patch, warming further as the surface pressure crashed inward. Not a broad, clear eye of the kind a mature, sprawling typhoon carries. A dot. That structure has a name, and forecasters do not use it casually. It is called a pinhole eye, an extremely small, clear, circular eye, typically well under 10 nautical miles across, sometimes only a few miles from one side to the other. And the reason forecasters react to the sight of one is statistical as much as physical. Pinhole eyes appear most often in storms that are rapidly intensifying at that exact moment. It is not a feature that shows up and then sits there. It is a feature that shows up while the storm is in the middle of doing something violent. Now, there is a complication in all of this that you need to know about, because it explains a lot of what happened next in the public conversation about this storm. Nobody flew into Dolphin. There is no routine aircraft reconnaissance in the Western Pacific. It ended in this basin in the late 1980s. In the Atlantic, when a hurricane threatens the United States, aircraft fly into the core and measure the pressure and the winds directly. Out here, in the busiest tropical cyclone basin on the planet. The intensity numbers are estimates derived from satellite imagery. The method used is called the Dvorak technique, and it is one of the more remarkable pieces of applied pattern recognition in the atmospheric sciences. Developed in the 1970s, it assigns a storm a number, a T number, based on the arrangement, the size, and the temperature contrast of its cloud features. A storm with a ragged central dense overcast and no eye gets a low number. A storm with a small, warm, well-defined eye surrounded by a tight ring of very cold convection gets a high one. Those numbers map to intensity estimates. What makes the technique remarkable is not that it works. It is that it was built before anyone could model these storms properly, out of nothing but thousands of hours of a human being looking at satellite imagery and noticing that storms of similar intensity kept producing similar-looking patterns. It is empirical in the oldest sense of the word. It also comes with a set of rules about how fast a storm's number is allowed to change between analyses, because the technique was designed around storms that evolve at ordinary rates. Those constraint rules are sensible almost all of the time. They're also exactly the wrong tool for a storm that reorganizes in 5 hours, because the method is built to resist believing that a storm changed that much that quickly. There is a second, more physical problem with reading a pinhole storm from space. Satellite intensity estimation depends on measuring the temperature difference between the eye and the surrounding eye wall, and to measure the temperature of the eye has to be big enough for the sensor to resolve it cleanly. A pinhole eye a few miles across occupies only a handful of pixels on the imager being used to analyze it, and some of those pixels are contaminated by the very cold eye wall right next to them. The measured eye temperature comes out too cold, the contrast comes out too small, and the technique's answer comes out too low. The storms most likely to be underestimated from space are, by the mechanics of the method, the strongest and fastest developing ones. The scale effectively tops out around T8.0, which corresponds to roughly 170 knots of sustained wind. When forecast discussions around Dolphin raised the possibility of the storm reaching T8.0, they were not picking a dramatic-sounding number. They were saying it might reach the top of the scale we use to measure these things from space. And this is where the gap opened up. For a period on July 28th, the official advisory carried Dolphin at 120 km per hour, a low-end typhoon, while meteorologists analysing the same satellite imagery independently were estimating the storm was already at Category 3 to 4 equivalent intensity, and possibly higher, not because anyone was wrong. Because the storm was changing faster than a fixed advisory cycle can be updated. Hold on to that gap. It comes back twice more in this story, once as a scientific problem and once as something else entirely. The image told everyone that the eye had gotten very small. What the image cannot tell you is why small means strong. Part 4. The figure skater problem. Every explanation of this you will ever hear starts with a figure skater, and there is a reason for that. The analogy is not a simplification. It is the same physics. A skater spinning with their arms extended pulls those arms in toward their body and immediately spins faster. Nobody pushed them. No additional energy went into the system. What happened is that angular momentum, the rotational equivalent of ordinary momentum, is conserved. Angular momentum depends on both how far something is rotating and how far its mass sits from the axis of rotation. Pull the mass inward, reduce the radius, and the rotation rate has to increase to compensate. It is not a choice the skater makes. It is arithmetic that the universe enforces. Now put that inside a typhoon. Air spiraling inward toward the center of a tropical cyclone is doing exactly what the skater's arms are doing. It starts hundreds of miles out, rotating slowly around the center. As it moves inward, its radius shrinks, and to conserve angular momentum it must rotate faster. By the time it reaches the eye wall, the ring of thunderstorms surrounding the eye, where the air finally turns and goes vertical, it is moving at the storm's maximum wind speed. That is why the fastest winds in a hurricane are always found at the inner edge of the eye wall. It is the smallest radius the inflowing air reaches before it goes up, which means the size of the eye is not a cosmetic detail. It is the radius at which the spin-up stops. Here is what I want you to take away from this entire video, and it is the thing that makes 5 hours possible. A storm with a contracting eye wall does not need more energy coming in to produce stronger winds. It can take the same inflow it already had and simply wind it tighter. The storm is not being fed harder. It is being wound tighter, and rearranging a storm's geometry can happen far, far faster than accumulating additional energy can. That is the answer to the question I left hanging at the end of the first part. 5 hours is not enough time to add a meaningful amount of new energy to a system the size of a typhoon. But 5 hours is more than enough time to change its shape. The pressure side of this works in parallel. As the core organizes and that warm, subsiding column deepens, the surface pressure at the center falls. That deepens the difference between the pressure at the center and the pressure in the surrounding environment, and it is that difference, the pressure gradient, that physically drives the wind. Steeper gradient, faster wind. When Dolphin's pressure crashed inward, forecasters were watching the gradient steepen in real time, and once that starts, there is a feedback loop that takes over, and it is the reason these storms can run away from the forecast. It works like this. Faster winds across the sea surface increase evaporation, because evaporation depends strongly on wind speed. More evaporation means more water vapour being lifted into the eye wall. When that vapour condenses into cloud droplets in the rising air, it releases latent heat, the energy that was absorbed when the water evaporated in the first place. That heat release warms the core of the storm. A warmer core means lower surface pressure. Lower pressure means a steeper gradient. A steeper gradient means faster winds. And faster winds mean more evaporation, which starts the whole cycle over again, one notch higher. That loop has a name in the literature, the wind-induced surface heat exchange feedback, and when it catches cleanly, a storm can climb for as long as the conditions hold. The obvious question is why it does not catch in every storm, since the ingredients are common. And the answer is that the loop is fragile in a very specific way. Vertical wind shear tilts the vortex so that the top of the storm sits downstream of the bottom, which breaks the vertical alignment the loop needs and lets dry environmental air get in at mid-levels. Dry air entrained into the core evaporates cloud droplets, which absorbs heat rather than releasing it, and cools and weights the air until it sinks, the exact opposite of what the eye wall needs. A shallow warm layer in the ocean lets the storm churn up cold water and cut its own evaporation off at the source. Any one of these will break the loop, and in most storms, at least one of them is present. This is also where the word symmetry finally earns its importance. If convection is only firing in one quadrant of the storm, the downshear side typically, the feedback is only running around part of the circle. Heat is being released in one place and not another. The core cannot warm evenly, and the pressure fall is limited. When convection wraps completely around the center with uniform symmetry, the loop runs all the way around. Every part of the ring is contributing. There is one further ingredient that rarely gets mentioned and matters enormously, which is the storm's own history. A tropical cyclone that has spent 2 days being knocked around by shear carries the damage with it. A broad, messy, tilted circulation takes time to repair, even after the hostile conditions clear. A storm that consolidates early, on the other hand, arrives at the favourable environment already assembled and can start converting immediately. Structure is not just about the conditions the storm is in today. It is about what the storm was allowed to build before today. Dolphin had all of it at once. Complete wrapping, uniform symmetry, no dry air intrusion, low shear, a stacked vertical circulation, water above 29 degrees Celsius, which we will come back to because the surface number is not the important one. Every condition the feedback requires, present simultaneously, over an ocean with nothing in the way. And this is exactly why the intensification problem is so difficult, and why it remains, 4 decades into the satellite era, the single largest standing gap in tropical cyclone forecasting. The permission conditions are diagnosable. Forecasters can see warm water and low shear on a map a day or two ahead, and they will tell you, correctly, that rapid intensification is possible. What they cannot tell you is the moment the feedback catches, because that depends on the storm's internal structure at scales the models struggle to resolve, and on whether the eye wall happens to contract, and on 100 small things happening inside a core that satellites can only look at from above. It is worth being concrete about how lopsided that improvement has been, because it is one of the quiet successes of applied science, and it makes the remaining gap look even stranger. Over the last 30 to 40 years, average track forecast errors have fallen by well over half at every lead time. A 3-day track forecast today is more accurate than a 1-day forecast was in the early 1980s. That is why hurricane evacuations now happen on the right stretch of coastline instead of the wrong one, and it is a genuine, measurable, lives-saved achievement built on better satellites, better models, and vastly more computing power. Intensity forecast errors over the same period improved too, but nothing like as much, and the improvement is concentrated in the easy cases. Storms doing ordinary things at ordinary rates. We have always believed the hard part of forecasting a hurricane is figuring out where it will go. But the place these forecasts still break is not the map. It is the clock. 5 hours is fast, but fast compared to what? There is an answer to that, a specific one with a number attached. It was set in this same ocean 43 years ago by a storm that almost nobody has ever heard of. Part 5, September 1983. 976 hectopascals to 876 hectopascals. That is the record. 100 hectopascals of pressure fall in a little over 23 hours, measured in the Western Pacific in September of 1983 by a storm named Forrest. If that number does not immediately land, let me translate it. The average sea level pressure on Earth is a little over 1,000 hectopascals. A strong winter storm crossing the North Atlantic might bottom out near 950. A serious hurricane might reach 920. Forrest fell 100 hectopascals, a tenth of the entire weight of the atmosphere above the storm, in the span of a single day and night. What a pressure fall actually represents, physically, is mass being removed. Atmospheric pressure at any point on the surface is simply the weight of all the air stacked above that point. When the pressure at the centre of a storm drops by 100 hectopascals, it means roughly a tenth of the air column over the centre has been evacuated, lifted up through the eye wall and thrown outward at the top of the troposphere and not replaced. The storm is, in a very literal sense, digging a hole in the atmosphere and throwing the material away, and the wind is the atmosphere trying to fill that hole. The steeper the walls of the hole, the harder the air rushes in. That is the entire relationship between pressure and wind, and it is why the pressure number is the one meteorologists take most seriously, because unlike wind speed, which is a single value measured at a single point, pressure describes the state of the whole system. Forrest holds the World Meteorological Organization recognized record for the fastest intensification of a tropical cyclone anywhere on Earth. But the detail that makes it genuinely remarkable, rather than a piece of trivia, is that it did not set the record once. It set it 3 times. Forrest also holds the record for the greatest intensification over a 36-hour window and over a 48-hour window. It did not catch one lucky day. It sustained the rate for 2. The scientific literature on Forrest describes it, quite directly, as the overlooked record holder. A storm that established the benchmark for intensification in 3 separate time frames and then more or less vanished from public memory. There is no documentary, there are no anniversary retrospectives. Ask 100 people to name the fastest intensifying storm in history, and you will get Katrina, or Patricia, or Haiyan, and not one of them will say Forrest. Some of that is simply timing. 1983 was before the age when a storm's satellite loop could be watched live by millions of people on a phone. A typhoon in the open Western Pacific, threatening no populated coastline at the moment of its peak, produced a set of numbers that went into an archive and stayed there. The event that mattered scientifically and the event that mattered publicly were not the same event, and only one of them got remembered. What Forrest has instead of a legacy is a pressure trace, a line on a chart falling almost vertically, and how that trace was made is the part of this story that matters most for Dolphin, because it changes what any comparison between them can honestly claim. Forrest's pressure was measured, not estimated. In 1983, the United States military flew routine reconnaissance missions into Western Pacific typhoons. Aircraft that entered the storm penetrated the eye wall and recorded the minimum surface pressure directly with instruments in the aircraft and with drop-ons released into the core. When the record says 976 to 876, it is describing readings taken by instruments physically inside the storm. It is worth understanding what those flights actually involved, because the phrase "flew into the storm" does a lot of quiet work. A reconnaissance aircraft approaching a typhoon does not fly over the top of it. It flies through the eye wall, at altitude, into the most violent sustained turbulence in the atmosphere, and comes out the other side into the calm of the eye. Then it turns and does it again, crossing the storm along a different axis, building a picture of the pressure and wind field from the inside. Along the way, the crew releases drop sondes, instrument packages that fall on small parachutes, radioing back temperature, humidity, pressure and wind every fraction of a second on the way down until they hit the sea surface. That is where a directly measured minimum central pressure comes from, a specific instrument at a specific moment physically inside the thing being measured. That program ended. Routine aircraft reconnaissance in the Western Pacific was discontinued in the late 1980s, and it has never returned. The reasoning at the time was, broadly, that the satellite era had arrived and that the estimates it produced were adequate for the operational job of warning people. And for track forecasting, which is what saves the most lives, that judgment has largely been vindicated. Every typhoon in this basin since then, including every storm that has been called the strongest on record by anyone, has had its intensity estimated from satellite imagery rather than measured from inside. Sit with the consequence of that for a moment, because it is genuinely uncomfortable. The most active tropical cyclone basin on the planet, the basin that holds the world record for intensification and the world record for lowest pressure ever measured, has had no routine direct measurement of storm intensity for roughly 35 years. Everything we say about how strong these storms get, we say from 400 miles up. So when dolphins' numbers are compared to forests, the comparison is not apples to apples. It is an estimate being compared to a measurement. And satellite estimates of pinhole-eye storms, as we established, are the estimates most likely to be wrong, usually wrong low. That cuts in an interesting direction, and I want to be careful about it rather than dramatic. It does not mean dolphin is secretly stronger than the record. It means the honest answer about where dolphin sits relative to forest will not exist this week or next week. It will exist in a post-season reanalysis document published months from now, after analysts have gone back through the entire satellite record and reconciled the estimates. This is the thread running underneath the whole story. We are watching something happen in real time that we cannot actually measure in real time. The forecast can tell us what might happen. The satellite can tell us what the cloud pattern looks like. The one thing nobody can give us right now is a number we can trust. 43 years after a forgotten storm set a record with instruments flown into its eyewall, we are watching a storm that may be doing something comparable, and we are watching it through a technique that struggles most with exactly this kind of storm. That is not a failure of anyone's competence. It is a gap in what we chose to keep measuring. Part 6. The Storms That Came Close. The record has been approached 3 times, not broken, approached. In October of 2015 in the Eastern Pacific, a hurricane named Patricia dropped its central pressure by 97 hectopascals in 24 hours, 3 hectopascals short of forest. 3. Patricia's peak numbers are the ones people remember, and they deserve to be remembered. Minimum pressure of 872 hectopascals, maximum sustained winds of 215 miles per hour. It remains the most intense tropical cyclone ever recorded in the Western Hemisphere, and among the most intense recorded anywhere. The peer-reviewed analysis of what Patricia did was published in the Bulletin of the American Meteorological Society in 2017, and the title of that paper is the reason we are talking about record books at all in this video. It was called Rewriting the Tropical Record Books, The Extraordinary Intensification of Hurricane Patricia. Scientists do not usually name papers like that. The choice of title tells you how the research community reacted to what they had just watched. There is a detail about Patricia that almost never makes it into the retelling, and it is the reason 2015 is remembered as a record rather than a catastrophe. Patricia made landfall on a stretch of the Mexican Pacific coast that is mountainous, sparsely populated, and lacking any major city directly in the path. The terrain tore the storm apart with extraordinary speed once it came ashore. Had the same storm at the same intensity come ashore 200 miles in either direction, the 2015 event would be remembered the way Katrina and Haiyan are remembered, and the scientific paper about its intensification rate would be a footnote to a disaster rather than the headline. The most intense hurricane ever recorded in this hemisphere is primarily a scientific story because of geography. What the researchers found, in careful language, was that Patricia had intensified at a rate near the upper bound of what the physics permits, in an environment that was close to ideal in every measurable way. What they were careful not to claim was that Patricia was caused by anything in particular, or that its rate was unprecedented in the true sense. Forrest's number still stood. What Patricia demonstrated was that the ceiling Forrest established was not a fluke of measurement from a bygone era. It was a real physical limit, and a modern storm with modern observations had come within 3 hectopascals of it. 4 years later, in October of 2019, Super Typhoon Hagibis did it again. 98 hectopascals in 24 hours. 2 off the record, and Hagibis did it in the Northwest Pacific, the same basin as Forrest, the same basin Dolphin is sitting in right now. Look at the pattern in those dates, and you will notice something. And I want to handle it carefully because it is the kind of observation that gets misused in both directions. The record was set in 1983. The 2 closest approaches to it happened in 2015 and 2019. 3 of the 4 fastest intensification events in the record occurred within the last 11 years of a record that spans many decades. That looks like a trend. It might be 1. But it is not automatically 1, and here is the honest complication. The observing system changed. Forrest was measured by aircraft. Patricia was measured by aircraft too, since the Eastern Pacific and Atlantic still have reconnaissance. Hagibis was estimated by satellite. The density and quality of observations, especially satellite coverage and resolution, have improved enormously over the last 4 decades. Some of what looks like more extreme storms is better detection of extreme storms. Any serious claim about trends in intensification rates has to deal with that problem head-on, and the good research does. We will come back to what that research actually found. There is one more storm that belongs in this list, and it belongs for a different reason. In October of 1979 in the Northwest Pacific, Typhoon Tip reached a minimum sea level pressure of 870 hectopascals. That is the lowest sea level pressure ever measured anywhere on Earth, in any weather system of any kind. Tip was also enormous. Its circulation spanned a substantial fraction of the entire Western Pacific basin, which makes it the strange twin of a pinhole storm rather than an example of one. A storm that large is not winding a small amount of air very tightly. It is drawing on an area of ocean so vast that the total energy passing through it dwarfs anything a compact system can assemble, and it converts that into an extraordinarily deep pressure minimum over a broad core. Wilma and Tip sit at opposite ends of the same spectrum. One reached an extreme by concentrating everything into a 2-mile eye, the other by gathering an ocean's worth of inflow. Both ended up in the record book. There is more than one route to the ceiling. So consider what that means about the ocean we are watching right now. The world record for how fast a storm can intensify was set in the Northwest Pacific. The world record for how intense a storm can get was set in the Northwest Pacific. Both records were set within 4 years of each other, both by storms measured directly by aircraft, and both still stand. Dolphin is intensifying in the same basin, over a warmer version of the same ocean, with no aircraft anywhere near it. It is also worth noticing what these storms have in common besides their numbers. Every one of them intensified over an area of unusually deep warm water. Every one of them did it in an environment with almost no vertical wind shear. Every one of them developed a compact symmetric core, and most of them developed a very small eye. And every one of them did the bulk of its deepening over open ocean rather than near land, because proximity to land introduces friction, dry air, and terrain effects that interrupt the process. The record book is not a collection of random extremes. It is a list of the same configuration, found repeatedly by different storms in different decades. Every storm on this list did the same thing Dolphin did on July 28th. Each of them found the configuration, caught the feedback, and ran. The difference between a record and a footnote is not whether the burst happens. It is how long the burst is sustained before something interrupts it, and that is the part worth sitting with. Not one of these bursts was predicted in advance at the rate it actually occurred. Not Forrest, not Patricia, whose forecast was revised upward repeatedly as it happened. Not Hagibis. The record book of tropical cyclone intensification is also, read another way, a list of the largest forecast failures in the history of the field. Part 7. The smallest eyes ever measured. In October of 2005, Hurricane Wilma developed an eye approximately 2 nautical miles across. 2 nautical miles, roughly 2 miles, about 3.2 kilometers, from one side of the eye to the other. It is the smallest eye ever observed in an Atlantic hurricane, and it may be the smallest ever observed anywhere with reliable measurement. Try to hold both halves of that image at once. Wilma's overall circulation at the time spanned hundreds of miles of the Caribbean, and at the centre of that was a pocket of calm, sinking air that you could have walked across in under an hour. A storm the size of a country, with a hole in the middle of it the size of a neighbourhood. On the 19th of October, during that same period, Wilma's central pressure reached 882 hectopascals, the lowest ever recorded in the Atlantic basin. Aircraft flew into it and measured that number directly. I want to draw the line between those two facts as clearly as I can, because it is the point of this entire part. The smallest eye ever measured in the Atlantic and the lowest pressure ever measured in the Atlantic belong to the same storm, on the same day, within hours of each other. That is not a coincidence, and it is not two separate records that happen to coincide. It is one physical event described in two different units. The eye got small because the eye wall contracted. The pressure got low because the eye wall contracted. Small eye and extreme intensity are the same phenomenon seen from two angles, which is exactly why forecasters looking at dolphins' imagery on July 28th reacted the way they did. There is a further consequence of a 2-mile eye that is worth stating explicitly, because it is where the danger of these storms actually lives. In a hurricane with a broad 40-mile eye, the wind speed falls off gradually as you move outward from the eye wall, and the change in wind across any given mile is modest. In a storm with a 2-mile eye, the entire wind field is compressed. You can go from calm air, with blue sky overhead, to the strongest winds on the planet in the space of a mile or two. Anyone standing at the edge of that eye experiences the full violence of the storm arriving essentially without transition, and then, after the eye passes, arriving again from the opposite direction. The gradient is not a curve, it is a wall. Wilma is not alone. In September of 2021, Typhoon Chanthu, in the Western Pacific, the same basin again, developed a pinhole eye of roughly 4 to 6 miles in diameter, with some estimates putting it near 5, while explosively intensifying to Category 5 equivalents on September 8th. The satellite loops from that event look almost identical in character to what Dolphin produced. A sudden, tiny, perfectly circular dot appearing in the middle of a cloud mass that had been solid a few hours earlier. And that is genuinely what it looks like to a forecaster in the moment. Not a dramatic clearing, a dot, sometimes only a handful of pixels across, appearing where there was nothing, and then warming rapidly image after image as the subsidence in the middle deepens. The observational problem this creates is the one we touched on earlier, and now I can give it its full weight. The satellite techniques used to estimate intensity were built around storms with resolvable structures. They were calibrated on the patterns that most storms produce. A core only a few miles wide sits close to the practical resolution limit of the imagery being used to analyse it, and the cold eye wall immediately adjacent contaminates the measurement of the warm centre. The technique is being asked to characterise a feature that is barely larger than the grid it is being measured on. There is an additional wrinkle that compounds it. The satellites watching this part of the Pacific are geostationary, parked over the equator, roughly 22,000 miles up, staring at the same face of the Earth continuously. That is what makes continuous storm monitoring possible at all, but a geostationary satellite views high latitudes and the edges of its disk at an angle, and the further a storm sits from the point directly beneath the satellite, the more distorted and elongated each pixel becomes on the ground. A feature a few miles across is being sampled by a measurement footprint that is not only large but skewed. This is a large part of why real-time intensity estimates of pinhole eye storms scatter so widely between different agencies. It is not that one agency is careless and another is rigorous. It is that when you feed the same marginal, under-resolved imagery into different analysis procedures, you get different answers, and the disagreement can easily amount to a full category of intensity. Which brings us straight back to the gap that opened up on July 28th, when the official advisory carried Dolphin at 120 km per hour, while independent analysts of the same imagery were placing it at Category 3 to 4 equivalent. That gap was not a mistake. It was the predictable output of a measurement system meeting the one kind of storm it handles worst. So here is where we stand. We know precisely what the record is and who holds it. We know what Dolphin's eye looks like. And we know that the tools available cannot resolve that eye precisely enough to tell us, in real time, how close to the record it actually is. The shape everyone is staring at right now is the same shape that appears in every single entry in the record book. That is why the forecast jumped. Not because anyone measured something, because everyone recognised something. Part 8. What Dolphin would have to do. Let us do the arithmetic, because it clarifies things enormously. Dolphin was at 980 hectopascals when it was upgraded to Typhoon status early on July 28th. To match what Forest did, It would have to reach roughly 880 hectopascals within 24 hours of that point. That's a storm going from a low-end typhoon to something in the neighbourhood of the most intense tropical cyclones ever recorded inside a single day. Is that physically possible? Yes, Forrest did it. Patricia came within 3 hectopascals of it. The physics permits it in an environment like the one Dolphin is sitting in. Is it what the forecast actually calls for? No, and the distinction matters. Guidance carrying the storm to 145 knots at 72 hours and discussions raising a ceiling near 170 knots describe an extraordinary intensification spread across roughly 3 days. The record requires the same magnitude of change compressed into one. Dolphin can produce a genuinely historic storm without producing a record rate storm, and those two outcomes will look almost identical on television. There is also a translation problem sitting inside the arithmetic, and it trips up almost every public discussion of storm records. Wind and pressure are related, but the relationship is not an equation. It is a statistical fit, and it differs by basin. Forecasters use what are called wind-pressure relationships, empirical curves derived from decades of storms in a particular ocean, to convert between the two. The Western Pacific uses different curves than the Atlantic, which is one reason the same storm can be described with different numbers by different agencies. More importantly, the relationship depends on the size of the storm. A very compact system can achieve an extremely low central pressure without carrying the enormous integrated wind field of a giant, because the pressure gradient is squeezed into a small radius. Conversely, a very large storm can hold an immense amount of total energy, while showing a higher central pressure. Tip: the lowest pressure storm ever measured was gigantic. Wilma, the lowest pressure Atlantic storm, was tiny at its peak. They arrived at similar extremes by opposite routes. Dolphin, at the moment, is on Wilma's side of that divide, a compact, contracted core, which means its pressure could fall faster than its wind field grows, and any comparison to a record defined in pressure will be sensitive to exactly which numbers get used. Now, the harder problem. Nobody is going to measure this. There is no aircraft reconnaissance in the Western Pacific. No plane will penetrate Dolphin's eyewall. No drop sonde will fall through its eye. No instrument will physically record its minimum pressure. Every number attached to this storm, the ones in the advisories, the ones in the news coverage, the ones being posted by analysts, the ones in this video, is an estimate derived from imagery collected by a satellite in orbit. That is not a criticism of the forecasters. It is a description of the observing system that exists. It is worth appreciating just how strange this situation is when you say it plainly. We can tell you the position of a spacecraft beyond Neptune to within a few kilometers. We can measure the mass of a mountain from orbit by watching how it bends the path of a satellite. And we cannot tell you, to better than about a full category, how strong the strongest storm on the planet is right now, because nobody is flying through it, and the only instrument watching is looking down through 200 miles of its own exhaust. What happens instead is post-season best track reanalysis. Months after a season ends, agencies go back through the complete satellite archive for each storm, apply the analysis techniques without the time pressure of an operational advisory cycle, incorporate any additional data that has surfaced and produce a final intensity history. That reanalyzed track is the official record. It frequently differs from what was said in real time, sometimes by a category, occasionally more in both directions. Storms get upgraded years later, storms get downgraded years later, so the honest conclusion, and I would rather give you this than a satisfying one, is that any claim made this week about whether Dolphin did or did not approach the intensification record is a claim the available data cannot support, not because anyone is hiding anything, because the measurement that would settle it does not exist and will not be made. The reanalysis process is not a formality either. It is genuinely painstaking. Analysts rebuild the storm's entire life cycle from the raw satellite record, cross-check the pattern-based estimates against any microwave imagery that caught the core structure, fold in ship reports, buoy data, scatterometer wind retrievals, and any land or island observations the storm happened to pass over, and reconcile the disagreements between agencies that were issuing different numbers at the time. What comes out the other end is the official history of the storm, the version that goes into the database, the version researchers use for trend studies, the version that determines whether a record was broken. And that version can take a year or more to appear. There is a second caveat, and it is almost annoyingly technical, but it decides records. The intensification record is defined over a fixed 24-hour window. A storm can intensify with genuinely historic violence, and still miss the record because its bursts straddled the boundaries of the windows being compared, or because its deepening happened in two surges separated by a lull. The record measures a specific interval, not an impression. This has a practical consequence that runs well beyond record keeping. If the intensity of a storm cannot be pinned down to better than a category in real time, then every downstream decision built on that number inherits the uncertainty. Shipping routed around a storm is routed around an estimate. Aviation reroutes are planned against an estimate. And if a storm like this one is ever 3 days from a populated coast, rather than 3,000 miles from anywhere, the evacuation decision, how many people, how far inland, how early, is made against an estimate that could be a category off in the dangerous direction. That is why the phrase "no land threat" at the top of an advisory is not a reason to look away from a storm like Dolphin. It is the only circumstance under which we get to study this behaviour without the study being an emergency. So what should you actually watch if the number is unavailable? Watch the eye. Whether it holds that pinhole shape or whether a second ring of convection appears outside it. Watch whether the forecast peak on Thursday is met, exceeded, or cut short. Watch whether the storm's wind field starts to broaden, because that broadening is the fingerprint of a specific process that we are going to spend a whole part on shortly. Those are things you can see. The number is a thing you cannot. And that is the deeper reason this record matters as a framing device. It is not really about whether Dolphin gets a line in a book. It is that the yardstick exposes exactly how much less we can say in the moment than we would like to about the thing we most want to know. None of this happens without the water, though. Not the record, not Dolphin, not any of it. And the water underneath this storm in the summer of 2026 is not the water Forrest ran on. Part 9. What's under the water? Sea surface temperatures beneath and ahead of Dolphin are above 29 degrees Celsius. That is about 84 degrees Fahrenheit. Bathwater warm, the number quoted in almost every piece of coverage this storm has received. And on its own, it explains almost nothing. I want to take that number apart because the misunderstanding built into it is the single most common error in how these storms get discussed publicly, and getting it right is the difference between understanding why Dolphin exploded and just repeating that the water was warm. A tropical cyclone is not a passive engine sitting on top of a fuel tank. It is a mixing machine. Its winds drag across the sea surface with enormous force, and that drag does not just push water sideways, it generates turbulence that reaches down through the upper ocean, stirring the layers together. Cold water from below gets pulled up. Warm water from the surface gets pushed down. The result is a phenomenon you can see directly in satellite measurements of sea surface temperature. A cold wake, a visible trail of cooled water stretching out behind the track of a strong tropical cyclone, sometimes several degrees colder than the surrounding ocean, and persisting for days. Now think about what that means for the storm creating it. A tropical cyclone extracts its energy from evaporation at the sea surface. Evaporation depends on the temperature of the water directly beneath the storm, and the storm is actively cooling the water directly beneath it, which means every tropical cyclone is, to some degree, in a race against its own exhaust, burning through the warm layer it is standing on, and cooling its own fuel supply as it goes. If that warm layer is thin, the race ends quickly. The storm churns up cold water within hours, evaporation rates fall, the latent heat supply to the eye wall drops, and the intensification stalls out no matter how promising the surface temperature looked at the start. This is why a great many storms sitting over water above 29 degrees Celsius never do anything remarkable. The surface said yes, the subsurface said no. There is a structural reason the ocean resists giving up its heat, and it has a name, the thermocline. In most of the tropical ocean, the upper layer is warm and well mixed by wind and waves, and beneath it the temperature drops sharply over a relatively short vertical distance before settling into the cold, dark, nearly uniform deep ocean that makes up the vast majority of the volume. That sharp transition is the thermocline, and it acts as a lid. It resists mixing, because moving cold, dense water upward across it takes energy. How deep that lid sits and how sharp it is determines how much warm water a storm has access to before it starts fighting the cold beneath. So the number that actually matters is not how warm the surface is, it is how deep the warmth goes. Oceanographers and tropical forecasters express this in two related ways. The first is the depth of the 26 degrees Celsius isotherm, the depth at which the water temperature falls to 26 degrees, which is roughly the minimum that will sustain a tropical cyclone. In a marginal part of the ocean, that isotherm might sit 30 or 40 meters down. In the best parts, it can sit well over 100 meters down. The second and more useful is tropical cyclone heat potential, an integrated quantity that adds up all the heat stored in the water column above that 26-degree isotherm. It is not a temperature, it is an amount. It answers the question that actually determines a storm's fate. How much warm water is there to burn through before this storm starts drinking cold water? And this is where the Western Pacific becomes the Western Pacific. The warm pool of the Western Tropical Pacific is the largest and deepest reservoir of warm water anywhere on Earth. It is the reason this basin produces more tropical cyclones than any other, the reason it produces the most intense ones, and the reason both the world intensification record and the world lowest pressure record were set here within 4 years of each other. A storm over the heart of that pool can churn the ocean as violently as it likes, and still find warm water underneath, because the warm water goes down and down. In the summer of 2026, that reservoir is not in its normal state. A subsurface warm Kelvin wave has been moving through the equatorial Pacific carrying temperature anomalies in the range of +6 to +7 degrees Celsius at depths between roughly 100 and 250 meters. Analysts tracking it have described it as possibly the strongest on record. A subsurface Kelvin wave is one of the more elegant things the ocean does, and it is worth a moment. Under normal conditions, the trade winds blow from east to west across the tropical Pacific, physically piling warm surface water up in the western part of the basin and holding it there, while cold water wells up along the coast of South America to replace what has been pushed away. The warm pool in the west is, in a sense, water stacked against a wall of wind. When those trade winds weaken, or reverse, in what is called a westerly wind burst, the wall comes down. The piled-up warm water sloshes back eastward along the equator as a subsurface wave, depressing the boundary between the warm upper ocean and the cold, deep ocean as it travels. That depressed boundary is exactly what a hurricane wants. It means a thicker layer of warm water and a 26-degree isotherm sitting far deeper than usual across an enormous stretch of the tropics. That is the machinery of an El Niño, and it is the machinery currently loading this basin. 4 days ago, in the video on the Atlantic that cannot start a storm while the Pacific keeps building them, we walked through what this same forcing is doing to the other side of the world, and back on the 12th, in the video on the warmest ocean ever recorded, we looked at the background state underneath all of it. June of 2026 was the warmest month in the history of the global ocean record, with a global sea surface temperature of 20.86 degrees Celsius measured on the 21st of June, and marine heatwave conditions covering roughly 82% of the world ocean, the second largest extent ever recorded. The director of the Copernicus Climate Service described the state of the ocean as uncharted territory. That is the water dolphin is running on, not warm water in general, that water in that state, with that much heat stacked beneath the surface, which produces the consequence that makes this storm's forecast so aggressive. Dolphin cannot cool its own fuel supply fast enough to stop itself. The self-limiting break that ends most rapid intensification events, the storm churning up cold water and starving its own evaporation, is not available here. It can mix the ocean as hard as it likes and keep finding warmth underneath. That is why forecasters were willing to carry guidance to 145 knots at 72 hours and to discuss a ceiling at the top of the satellite scale, rather than issuing the conservative forecast that instinct and long experience usually recommend. They were not being dramatic. They were reading a subsurface field that told them the usual break was missing, so we have both halves now. Structure decides how fast a storm can climb, the ocean decides how high the ceiling is. Almost every storm gets one of those and not the other. Dolphin got both at the same time, and exactly 24 hours before any of this happened, in a completely different ocean, a completely different storm got both of them too. Part 10. The Other Ocean. Friday, July 24th, 2026. A tropical depression forms in the eastern Pacific, roughly 700 miles southwest of the coast of Mexico. It is given the name Genevieve. Nobody outside the forecasting community pays much attention, because it is not forecast to hit anything. By Saturday evening it is a hurricane. At 8 in the evening Mountain Time on Saturday, its maximum sustained winds are 80 miles per hour. A Category 1, respectable, unremarkable. By 2 in the morning Mountain Time on Monday, its maximum sustained winds are 160 miles per hour. That is a doubling of maximum sustained wind speed in roughly a day and a half. And because the destructive force of wind scales with the square of the speed, doubling the wind speed means the storm ended that period with roughly 4 times the destructive potential it started with. At 5 o'clock Eastern Time on Monday morning, July 27th, Genevieve was formally classified as a Category 5 hurricane, with 160 mile per hour sustained winds and a central pressure of 925 hectopascals. It was the first Category 5 hurricane of 2026, and the first hurricane in the eastern Pacific to reach that intensity since Christie in 2024. It did not make landfall. The forecast never called for one. The practical consequences were hazardous marine conditions along parts of the Mexican Pacific coastline, dangerous swell and rip currents. Real hazards, but nothing resembling a disaster. Genevieve spent its peak over open water, threatening essentially nothing. That profile should sound familiar, because it is Dolphin's profile exactly, one ocean and 1 day removed. And it is worth naming the environment Genevieve found, because it is the same list we ran through for Dolphin. Warm water beneath it, low shear over it, moist air around it, a circulation that stacked itself vertically and stayed stacked, convection that wrapped the centre rather than firing off to one side. The eastern Pacific in late July sits in the part of its season when all of that comes together most reliably, and Genevieve got the full set. Then it did what a storm does when it gets the full set and nothing interrupts it. It converted heat into wind at close to the rate the physics allows, and it kept doing so until something inside the storm itself stopped it. And then, later the same day it reached the top of the scale, Genevieve weakened back to Category 4. I want to be precise about why, because the reason is the most important thing in this video. It did not weaken because it ran out of warm water. It did not weaken because wind shear found it. It did not weaken because it hit land or ran under dry air. Genevieve weakened because it entered an eyewall replacement cycle. The storm interrupted itself. Think about what that means in light of everything we have established. The contraction that produced the Category 5, the eyewall pulling inward, the angular momentum concentrating, the pressure crashing, is the same geometry that triggered the process which ended it. The storm did not fail. It succeeded so completely that the success became unstable. The mechanism that builds these storms contains its own limit, and the limit activates precisely when the mechanism has run furthest. So here is where that leaves Dolphin, stated as plainly as I can. 24 hours before Dolphin's burst, in a different ocean, over a different warm anomaly, under a different forecast office, the exact sequence Dolphin is now in ran all the way to completion. Rapid intensification, a contracted core, the top of the scale, and then an eyewall replacement cycle that took a category back off it within hours. That is not a prediction of what Dolphin will do. It is the single most relevant piece of evidence anyone has about what Dolphin might do, and it arrived 1 day early in high resolution, with full observational coverage including aircraft reconnaissance, because the eastern Pacific still gets flown. That last detail deserves more attention than it usually gets, because it produces a genuine asymmetry in what we know. Genevieve was reachable. Aircraft operating out of the Americas can get to storms in the eastern Pacific, and the National Hurricane Center's intensity numbers for that basin are anchored by direct measurement when the storms matter. Dolphin is not reachable. It is thousands of miles from any base that flies these missions, in a basin where the program was shut down decades ago. So the storm we can measure precisely is the one that threatened almost nobody, and the storm we can only estimate is the one now forecast to reach the top of the scale. That is not anyone's failure of will. It is a consequence of where the aircraft are, and it means the better documented storm of the two is the one that will be remembered less. Genevieve also gave us something else, which is a clean timeline. Because it was flown, we know roughly when the inner eye wall began to erode, roughly how long the transition took, and roughly how much intensity came off during it. That is the kind of detail that turns a statistical statement. Pinhole eyes often trigger replacement cycles into a concrete expectation with a clock attached. When forecasters looked at Dolphin's Pinhole eye on Tuesday, they were not consulting an abstraction. They had watched the same sequence play out in full, 48 hours earlier, in an ocean where the instruments could reach, and Genevieve and Dolphin were not the only things happening. During the same window, Hurricane Fausto was tracking westward toward Hawaii. In the western Pacific, earlier in July, Super Typhoon Barvey had already become the third Category 5 storm of 2026, passing near Guam and the Northern Marianas with sustained winds around 180 miles per hour. Before that, unusually early in the season, Super Typhoon Sinlaku had produced a Category 5 in a month, when the western Pacific does not normally produce them at all. So by the end of July 2026, the Pacific basins had produced multiple Category 5 equivalent storms, including an exceptionally early one, a mid-season one near United States territory, the Eastern Pacific's first in 2 years, and a storm currently forecast to become the Western Pacific's third super typhoon of the summer. Over the same stretch of the calendar, the Atlantic produced 2 named storms and 0 hurricanes. Put those 2 columns side by side and the asymmetry is almost absurd. On one side of the Americas, an ocean that has manufactured Category 5 storms in April, in early July, in late July, with another currently forecast to join them before the week is out. On the other side, an ocean that by the end of July had not managed to produce a single hurricane, in a season where the climatological expectation would already have several. Same planet, same month, same sun. The Marianas detail is worth pausing on as well, because it is the one place in this entire season where a Category 5 storm came near people who live under United States forecasting and emergency management. Earlier this month we covered exactly that, the typhoon bearing down on Guam and the Northern Marianas, and what it means for an island population of that size to sit in the path of a storm at that intensity. Genevieve and Dolphin have both spent their peaks over water. Bavy did not have that luxury. 2 oceans producing extreme, rapid intensification events within 48 hours of each other is uncommon. It is not unprecedented. The tropics are large, the season is long, and coincidences happen. But when you place it next to the rest of the pattern, the coincidence explanation gets harder to hold, because you're no longer explaining one strange week. You're explaining a season in which one hemisphere's storm basins are running hot, and another is switched off entirely. That is not the signature of 2 independent flukes. That is the signature of a shared background state doing the same thing to both basins from underneath, and the 2 Pacific basins are not really separate systems in the way the map suggests. The eastern and western Pacific are connected by the same equatorial ocean, responding to the same trade wind changes, warmed by the same subsurface wave moving east along the equator. A shift in the state of that ocean does not politely stop at the international dateline. It changes the amount of deep warm water available to storms across a stretch of the planet, spanning nearly half the circumference of the Earth. When 2 storms in that region do the same unusual thing in the same week, the boring explanation is that they were both handed the same conditions because they were, which moves the question. We started by asking why this storm. The evidence keeps pushing us toward a different question, which is why now? And it is worth noticing one more thing about both of these storms before we go on. Neither burst was forecast at the rate it actually occurred. Genevieve's intensity forecast was being revised upward in real time as it happened. Dolphin's was being revised upward in real time as it happened. 2 storms, 2 oceans, 2 forecast offices, 2 sets of models, 1 week, and in both cases the number in the advisory was chasing the storm rather than leading it. Part 11. 1 El Niño, 2 oceans. In June of 2026, NOAA declared El Niño conditions in the tropical Pacific, with 63% odds that the event would exceed plus 2.0 degrees Celsius at its peak. If it does, it will stand among the largest El Niño events since records of this kind began in 1950. As of late July, the Oceanic Niño Index sat at approximately plus 0.98. That index deserves a plain explanation, because it gets quoted constantly and understood rarely. It is a 3-month running average of sea surface temperature anomalies in a specific box of the Central Eastern Equatorial Pacific, called the Niño 3.4 region. Plus 0.98 means that box is averaging roughly 1 degree Celsius above its long-term normal. 1 degree does not sound like much. Spread across a slab of ocean thousands of kilometers wide, sustained for months, 1 degree is an enormous quantity of heat being handed to the atmosphere. The mechanism is the one we started building in the last part, and now we can finish it. Trade winds weaken. The warm pool that is normally piled up in the west sloshes eastward. Upwelling of cold water along the South American coast shuts down, and the ocean, instead of holding its heat beneath the surface where it has been accumulating, begins venting it into the atmosphere across an enormous area. That heat does not stay in the tropics. It reorganizes atmospheric circulation across the entire planet, which is why an El Niño rearranges weather in places that have never heard of the Niño 3.4 region. The path it takes is worth understanding, because it explains why a temperature anomaly in one box of ocean can change the weather over a different continent. Warm water heats the air above it, that air rises, and the rising column of air shifts the position of the tropical thunderstorm belt. Shifting that belt is like moving the anchor point of a rope that is tied to the rest of the atmosphere. The jet streams respond, ridges and troughs set up in different places than they otherwise would, and storm tracks across the mid-latitudes get displaced for months at a time. That is why an El Niño winter looks different in California, in the southern United States, in Australia, in southern Africa, and in South America, all of it propagating outward from a change in where the tropical Pacific is putting its heat into the air. There is one more feature of these events that matters for storms specifically. El Niño tends to peak in the northern hemisphere late in the calendar year, which means the 2026 event has not finished strengthening. The index at plus 0.98 in late July is not the peak. It is a reading taken on the way up, with the western Pacific typhoon season still running and the subsurface heat still in place. For tropical cyclones specifically, it does two opposite things to two different oceans. Across the tropical Atlantic, an El Niño enhances upper-level westerly winds. That increases vertical wind shear over the main development region, the stretch of ocean between Africa and the Caribbean where most Atlantic hurricanes are born. And as we established, shear tilts a developing vortex, breaks its vertical alignment, and lets dry air into the core. It does not make storms impossible, it makes them fragile. Systems that would otherwise organize get pulled apart before they can close the feedback loop. 4 days ago, we spent a whole video on what that looks like from the Atlantic side. 2 named storms for the season, 0 hurricanes, the quietest start in over a decade, and a National Hurricane Center outlook forecasting no formation anywhere in the basin over a full week. The point worth carrying forward is that the empty Atlantic and the overloaded Pacific are not two separate stories. They are the same forcing, seen from two sides of a continent. Across the Pacific, the effects run the other way. The favourable environment expands eastward and southward. The area of deep, warm water available to storms grows. Shear over large parts of the basin drops. And the westerly wind bursts that help drive the El Niño in the first place also spin up tropical disturbances directly, because a burst of westerly wind meeting the prevailing easterlies creates exactly the rotational shear that seeds a tropical low. That is a genuinely satisfying piece of physics, and it is worth sitting with. The same wind bursts that build the subsurface warm wave which will feed the next generation of storms are also the wind bursts that create those storms. The fuel delivery system and the ignition system are the same mechanism. Analysts identified precisely that setup. A strong westerly wind burst sitting over warm surface anomalies and robust subsurface heat, as the trigger behind the season's earliest Category 5. The seasonal projections reflect all of it. Forecasters projected an above-normal northwest Pacific season of roughly 27 to 29 tropical storms or typhoons for 2026, with the possibility of the most active season since 2015. 1997 is the comparison most often reached for, because it was the last event that developed with this kind of subsurface signature at this point in the calendar. But the comparison comes with a caveat that changes its meaning. The Western Pacific in 2026 is warmer than it was during past very strong El Niño events at the same stage. The same atmospheric machinery is running, but it is running over a hotter ocean than the one that produced the 1997 season. That distinction is the one I want you to carry out of this part, because it is where the two halves of this story finally join. An El Niño does not create heat. It redistributes heat that is already in the climate system, moving it from beneath the surface of the Western Pacific into the atmosphere and out across the world. It is a redistribution event, and it reverses. In a year or two, the trades will strengthen again, cold upwelling will resume, and the index will fall back through 0 and go negative. The warming baseline is a different thing entirely. It is heat being added to the system and retained. It does not reverse on a 2-year cycle. And it means that when the next El Niño arrives, it will redistribute a larger quantity of heat than this one from a warmer starting point. The two are stacking right now. The redistribution event is running on top of the accumulation. Only one of them goes away next year. There is a useful way to picture the difference. Imagine a bathtub with the tap running slowly. El Niño is what happens when you slosh the water in the tub from one end to the other. One end gets deeper, the other gets shallower, and the total amount of water has not changed at all. The warming baseline is the tap. It is not sloshing anything. It is adding. And when you slosh a tub that has been filling for decades, the high end of the slosh reaches a level the tub has never seen before, even though the sloshing itself is completely normal behavior. That is why the 1997 comparison is useful and misleading at the same time. The atmospheric machinery in 2026 is doing something recognizable. Meteorologists know what an El Niño of this size does, and they can anticipate a great deal of it. What they cannot look up in the historical analogues is what that machinery produces when it runs over an ocean carrying decades of additional stored heat. And the practical result for storms is a raised floor under every measurement. An ordinary El Niño year now delivers ocean conditions across the tropical Pacific that would have been considered extraordinary 2 decades ago. The warm pool is deeper, the isotherm sits lower, the heat potential is higher, which means more storms in more places get handed the configuration that lets the feedback loop run without a break. None of that predicts which storm goes vertical, not one bit of it. It cannot tell you that Dolphin specifically would be the one to find the perfect arrangement on the 28th of July. What it explains is why so many storms are getting the chance. Part 12. The ceiling is moving. There is a theoretical maximum intensity that any tropical cyclone can reach in a given environment, and it can be calculated from first principles. That framework is called maximum potential intensity, and the version most widely used was developed by Kerry Emanuel at the Massachusetts Institute of Technology. Its central insight is that a hurricane is not really a weather system in the way a cold front is a weather system. It is a heat engine. A heat engine, in the thermodynamic sense, is any device that takes heat from a warm reservoir, converts part of it into mechanical work, and dumps the remainder into a cold reservoir. A car engine does this, a power station does this, and a tropical cyclone does this at a scale that dwarfs both. Walk the cycle. Air spirals inward toward the storm's center, at low altitude, moving across a warm sea surface, picking up heat and moisture the entire way. That is the intake stroke, and the warm reservoir is the ocean. The air then rises violently in the eye wall, and as the water vapor it carries condenses into cloud, the latent heat absorbed during evaporation is released into the atmosphere. That heat release is what drives the ascent and warms the core, and the resulting pressure fall is what generates the wind. That wind is the mechanical work the engine produces. At the top, roughly 10 to 15 kilometers up, the air flows outward away from the storm, radiating its remaining heat away to space at very cold temperatures. That is the exhaust, and the cold reservoir is the upper troposphere. Then the air sinks, slowly, over an enormous area, and the cycle closes. What sets the efficiency of any heat engine is the temperature difference between the two reservoirs. Warmer intake, colder exhaust, higher efficiency, more work extracted per unit of heat, which produces a conclusion that is simple to state and easy to misuse. Warming the ocean surface raises the theoretical maximum intensity a storm can achieve in that environment. A hotter, warm reservoir means a more efficient engine and a higher ceiling. Now the essential caveat, and I want to give it real weight rather than a passing nod, because it is what separates careful thinking from alarmism. Almost no storm ever reaches its potential intensity. The gap between the theoretical ceiling and what storms actually achieve is usually large, and it is large because reality keeps intervening. Shear tilts them. Dry air poisons them. Land destroys them. Their own eye wall replacement cycles interrupt them. Their own cold wakes starve them. Most tropical cyclones spend their entire lives well below the ceiling and then dissipate without ever approaching it. Raising the ceiling does not raise the average. What it does is raise the maximum available to the rare storm that manages to avoid every one of those interruptions. That is a subtle point, and it is worth making concrete. because it is where most public arguments about hurricanes and warming go wrong in both directions. Picture the intensity every storm in a season achieves plotted as a distribution. A great many weak systems, fewer moderate ones, a small number of intense ones, and a tiny handful at the extreme end. Raising the theoretical ceiling does very little to the crowded part of that distribution, because those storms were never limited by the ceiling in the first place. They were limited by shear, or dry air, or land, or their own structure. Where a higher ceiling shows up is in the thin tail on the far right, populated by the rare storms that dodge everything. Those storms were the ones actually running into the limit, raise it, and they go further. So the honest expectation is not that every storm gets stronger. It is that the strongest storms get stronger, and that the extreme end of the distribution stretches while the middle barely moves, which is exactly the kind of change that is easy to dismiss in any individual season and impossible to ignore over decades. Dolphin on July 28th was a storm avoiding every one of those interruptions. So what does the observational record actually show about whether this is happening? Not the theory, the measurements. The most cited work here is by Bhatia and colleagues, published in Nature Communications in 2019. They examined tropical cyclone intensification rates in the Atlantic across the observational record and found significant increases that are highly unusual compared with model-based estimates of internal climate variability. That phrasing is deliberately careful, and the care matters. They were not simply reporting that storms have been strengthening faster. They were testing whether the observed trend could plausibly be produced by the climate system's own natural swings, and concluding that it is unlikely. It is also worth understanding why the Atlantic is where this question gets asked, given that everything else in this video is happening in the Pacific. The answer is boring, and it is about data. The Atlantic has the longest, most consistent, most heavily aircraft-sampled tropical cyclone record on the planet, precisely because storms there threaten North America and have been flown into routinely for the better part of 80 years. If you want to test a claim about trends in storm behaviour, you go where the measurements are least contaminated by changes in how the measuring was done. The irony is not lost on anyone. The basin producing the extraordinary storms this week is the one where the record is weakest, and the basin where the record is strongest is the one that has not managed a hurricane all season. That distinction is the entire game in attribution science. Natural variability is large, noisy, and capable of producing decades-long trends that mean nothing. The only way to say anything meaningful is to ask how big a trend the system could produce on its own, and then check whether the observed one exceeds it. Bhatia and colleagues found a detectable signal, a trend large enough that natural variability struggles to account for it. Related research links large positive changes in intensification rates to large increases in sea surface temperature, and projects higher intensification rates by the end of this century relative to today. The physical chain is not exotic. Warmer water, higher potential intensity, and a greater probability that a storm which finds a favourable structure can run further before hitting a ceiling. So here is the framing I think is actually honest, and it is neither of the two you will usually be offered. No single storm proves anything. Dolphin is not evidence of climate change, and anyone telling you it is has skipped several steps. Individual storms are weather. Weather is noise. You cannot read a climate signal off 1 week of it, in either direction. But the distribution these storms are drawn from has moved. The ocean they form over set a global heat record 6 weeks ago. The subsurface anomaly feeding this basin is described as possibly the strongest on record, and peer-reviewed work finds intensification rates increasing beyond what natural variability comfortably explains. Dolphin is not proof of anything. Dolphin is what the tail of the new distribution looks like when you happen to be watching it. And that leads somewhere genuinely uncomfortable. If rapid intensification is becoming more common, while remaining the specific thing forecasters cannot predict, then the gap between what a storm is capable of doing and what we can warn people about in time is not closing. It is widening. Which brings the question back to this storm, in this ocean, this week, and to the single feature that could end its run before Thursday ever arrives. Part 13. The weakness built into the strength. The thing that made Dolphin dangerous is the thing most likely to take it apart. That is not a poetic construction. It is a structural fact about how these storms work and it is the reason the forecast for Thursday should be read as a branch rather than a number. Start with the statistics, because they are unambiguous. Eyes smaller than roughly 10 nautical miles frequently trigger eye wall replacement cycles, and storms with pinhole eyes are prone to large fluctuations in intensity, not fluctuations upward, but fluctuations in both directions, sometimes within the same day. The record of pinhole eye storms is not a record of steady climbs, it is a record of spikes and collapses. Here is the process step by step, because it is one of the most consequential sequences in tropical meteorology, and it is rarely explained properly. A mature, intense tropical cyclone is not just a single ring of thunderstorms around an eye. Outside the eye wall there are spiral rain bands, and those bands carry their own convection and their own rotation. Under certain conditions, one of those outer bands begins to organize into something more than a band. It closes up. It wraps around the storm at a larger radius than the eye wall, and it becomes a second concentric ring of deep convection surrounding the first. Now the storm has two eye walls, and they are competing for the same fuel. The inflow feeding the inner eye wall, the warm moist air spiraling in at low levels, has to pass through the outer ring to get there, and the outer ring is doing exactly what the inner one does, lifting that air, condensing its moisture, releasing its heat. The moisture gets taken out before it arrives. The inner eye wall, cut off from its supply, begins to starve. What follows is not gradual. The inner eye wall erodes, warms, loses its convection, and collapses. On satellite imagery, the tiny pinhole eye becomes fuzzy, then broad, then indistinct, and the storm that looked like a needle looks like a donut. The intensity consequence is measurable and consistent. Peak winds typically drop on the order of 20 to 30 knots through the cycle. But something else happens at the same time, and it is the part that matters most for anyone in the storm's path. The wind field broadens. The maximum winds now occur at the radius of the outer eye wall, which is larger. So the area experiencing hurricane-force wind expands, even though the peak value at the centre has come down. The storm gets weaker at its worst point and bigger everywhere else. Then, often, it rebuilds. The outer eye wall begins to contract. The same angular momentum argument applies all over again, and the storm re-intensifies. Sometimes it exceeds its previous peak. Sometimes it never gets back there. Which of those happens depends on how much warm water is left, how much shear has moved in, and how much time remains before landfall or cooler water intervenes. The underlying mechanism has been mapped in the research literature in considerable detail. Small-scale disturbances known as vortex-Rossby waves develop out of the horizontal wind shear at the primary eye wall. The sharp change in wind speed across the eye wall generates instabilities, and those instabilities propagate as waves through the vortex. A new outer eye wall can develop when these disturbances become phase-locked with the horizontal wind and propagate radially outward to a critical radius where angular momentum concentrates and convection can organize, and then the closing act, which is the exact mirror of the contraction that produced the peak. After the replacement completes, absolute angular momentum decreases at the outer eye wall expands and intensity falls. The same conservation law that spun the storm up when its radius shrank spins it down when its radius grows. The physics does not care which direction you run it. There is one more fragility that applies specifically to the very smallest eyes, and Dolphin is squarely inside it. As an eye wall shrinks to very small diameters, any disruption to the inner circulation can destroy the entire eye wall quickly, producing a rapid decrease in wind intensity. A large eye wall is a big, robust structure that can absorb a disturbance in one quadrant and keep running. A 2-mile eye wall has almost no margin. A dry intrusion, a patch of shear, a slight tilt, an outer band getting organized at the wrong moment. Any of these can take out a substantial fraction of the structure at once. The same geometry that lets a pinhole storm accelerate leaves it one perturbation away from collapse. Which is why Genevieve, 2 days earlier, is not an anecdote. It is a worked example with the answer in the back of the book. Genevieve reached the top of the scale and then dropped a category within hours, for exactly this reason, in a basin with aircraft flying through it and full observational coverage. There is a practical detail about how forecasters actually catch this happening, and it explains why the warning often comes late. Ordinary infrared satellite imagery, the kind that shows the cloud tops, is not very good at revealing a second eye wall forming underneath. The cirrus canopy spreading out above the storm hides the structure below it. What does reveal it is microwave imagery, which sees through the upper cloud shield to the rain and ice in the eye walls themselves, and shows concentric rings with startling clarity when they exist. The problem is that microwave imagery does not arrive continuously. It comes from instruments on polar orbiting satellites, which pass over a given point on the Earth only at intervals, and depending on the orbital geometry, those intervals can leave gaps of several hours over a specific storm. So a forecaster may know exactly what the core looked like at one moment, and then have to wait for the next pass to find out what it is doing now. In a storm that reorganized itself in 5 hours, a gap of several hours is not a minor inconvenience. It is potentially the entire event. For forecasters, this is not a curiosity. The eyewall replacement cycle is one of the largest sources of short-term intensity forecast error there is. A storm that is going to complete a cycle in the next 12 hours, and one that is going to keep intensifying look nearly identical in the moment. The difference between them is happening inside the core, at scales that operational models struggle to resolve, and the outcome can be a 30-knot swing in either direction, and the consequence of that reaches well beyond record books. Consider a storm approaching a coastline. If it completes an eye wall replacement cycle offshore, it may arrive with a lower peak wind speed and a wider wind field. That sounds like good news, and in terms of the maximum gust it is. But storm surge, which kills far more people than wind does, is driven by the size of the wind field and how long the wind has been pushing water in the same direction, not just by the peak value at the centre. A broader, slightly weaker storm can push more water ashore than a compact, slightly stronger one. The headline number goes down and the flooding goes up. So the honest forecast for Dolphin is not a number, it is a branch. Branch 1, the eye holds, the feedback keeps running, the storm climbs into the range the guidance describes, and we end up with a genuine record candidate that nobody will be able to verify for a year. Branch 2, an outer ring organises, the pinhole eye collapses, the storm drops 20 to 30 knots, broadens, and then either rebuilds or does not, and the record conversation ends quietly, without anyone ever finding out how high it could have gone. Both branches are entirely consistent with everything visible right now, and there is one small piece of land close enough to care which one the storm takes. Part 14. The only land within reach. Wake Island is an atoll in the middle of the Pacific, roughly midway between Hawaii and Japan. Its highest point stands about 20 feet above sea level. It has an airfield, a United States Air Force installation, and a scientific outpost, and its population consists entirely of military personnel and Department of Defense contractors. There are no towns. There is no hospital of consequence. There is nowhere to go that is more than a few feet above the ocean. Dolphin's forecast track carries it approximately 230 miles to the southwest of Wake at closest approach, with outer rain bands potentially reaching the island. On a map, 230 miles looks comfortable. It is worth understanding what an atoll actually is, because it explains the vulnerability better than any statistic can. An atoll is the ring-shaped remains of a coral reef that grew around a volcanic island which has long since subsided beneath the sea. What is left is a thin loop of coral rubble and sand enclosing a shallow lagoon. There is no high ground because there was never anything to make high ground out of. There is no interior to retreat into because the interior is water. The land itself is a few feet of accumulated reef debris sitting on top of a drowned mountain, and the ocean is on both sides of you at all times, the open Pacific on one, the lagoon on the other. That geometry is the reason a storm surge at an atoll behaves so differently from a storm surge on a continental coast. On a mainland shore, water pushes inland and eventually runs out of energy against rising terrain. At an atoll, there is nothing to run into. The water crosses the land entirely and pours into the lagoon from the outside, and the island effectively disappears beneath the sea for the duration. Wake Island has been through this before, and it is worth knowing exactly what happened, because it is the only concrete demonstration in this entire story of what a storm of this class actually does when it arrives somewhere. In late August of 2006, Super Typhoon Ioke approached Wake as a Category 5 system. On the 28th of August, the Air Force evacuated the island. All 188 residents, mostly American and Thai contractors working at the civilian base, were flown 3,700 kilometers to Hawaii aboard 2 C-17 Globemaster aircraft, and all operations were suspended. It was the first time the territory had been evacuated in nearly 30 years. 3 days later, on the 31st of August, the southwestern eye wall of Eoke passed directly over the island. The winds were well over 185 miles per hour. The storm drove a surge of roughly 20 feet and pushed waves directly into the lagoon at the centre of the atoll, which is to say, the ocean came in from the outside and filled the middle. When it was over, approximately 70% of the buildings on the island had been moderately to severely damaged. An assessment and repair team returned in September, restored limited function to the airfield, and over the following period the base was brought back to normal operations. Nobody died because nobody was there. The evacuation worked, and it worked because the forecast gave enough warning to fly 188 people, 3,500 kilometres before the storm arrived. That is the version of this story where everything goes right, and it is worth appreciating what everything going right required. It required a forecast confident enough, early enough, that a base commander was willing to shut down an installation and put every person on it into the air. It required aircraft to be available and able to reach a runway 3,500 kilometres from the destination. It required the decision to be made while the runway was still usable, because once conditions deteriorate, the airfield that is the only way off the island stops being an option, and the 188 people are simply on the atoll at 20 feet of elevation with a Category 5 storm inbound. There is no second plan. There is no drive inland. The evacuation window is defined entirely by the last moment an aircraft can safely take off. Now hold that against the thing this entire video has been circling. Eoke's approach was forecast with enough lead time to organise an evacuation across an ocean. What we have spent 2 hours establishing is that intensity forecasting is the piece that still fails, and that it fails specifically in the fast case. An evacuation from a place like Wake is planned against a forecast. If the storm in that forecast strengthens 2 categories faster than expected, or if the track shifts inside the forecast error while the storm is deepening, the plan that was adequate yesterday is not adequate today. 230 miles is a comfortable number on a forecast map. It is a thin one in reality. It sits well inside the range where a modest track adjustment changes the outcome entirely, and the guidance producing it is being generated for a storm that has already outrun its own advisory once this week. The point is not that Wake Island is in danger. On present guidance, it is not, and the most likely outcome by a wide margin is elevated surf, some wind, some rain, and an island that barely notices. The point is that this is what the stakes look like when the geometry does not cooperate, and that Eoke is not ancient history. It is inside the working memory of the people who run that airfield. Part 15. The Claims That Always Follow. Within hours of the intensification, the claims started. I want to handle this seriously rather than dismissively, because these ideas circulate every single time a storm does something dramatic, and simply mocking them has never once persuaded anybody of anything. The claims around Dolphin are the standard set: that the storm was manufactured, that it is being steered, that weather modification programs or ionospheric research facilities are responsible, and that a storm cannot intensify this fast naturally. Let us take the energy argument first, because it settles most of it in a single number. A mature typhoon releases latent heat on the order of 10 to the 19th power joules per day. That is a 1 followed by 19 zeros. To put that in terms that mean something, it is roughly equivalent to hundreds of times the entire electrical generating capacity of the world, running continuously for the whole day. Every day the storm exists. Nothing humans have built operates within orders of magnitude of that scale. Not close, not in the same conceptual neighbourhood. The question is not whether we could steer a typhoon. It is that the total energy available to every power station on the planet combined is a small fraction of what one storm burns through between one sunrise and the next. Cloud seeding deserves a fair hearing rather than a dismissal, because it is real. It exists, it is used operationally in a number of countries, and it has a genuine physical basis, introducing particles that give supercooled water droplets something to freeze onto. But the effects are marginal and local. Independent evaluations of seeding programs struggle to detect precipitation increases beyond a few %, and only under favourable conditions in specific cloud types. It is a technology for nudging a snowpack, not for constructing an eye wall. Ionospheric heating facilities come up constantly and are the easiest to address, because the objection is geographic before it is energetic. These facilities operate on the ionosphere, above roughly 80 kilometers of altitude. Weather, all of it, every cloud, every storm, every hurricane that has ever existed, happens in the troposphere, in the bottom 10 to 15 kilometers. The facilities are working on a completely different layer of the atmosphere, tens of kilometers above where any weather occurs, with power measured in megawatts against a storm-consuming energy, at a rate that dwarfs civilization. Now the second claim, which I take more seriously because it has a real hook in reality. The suppression claim says agencies are hiding the storm's true intensity, and the hook it attaches to is genuine. For several hours on July 28th, the official advisory said 120 km per hour, while independent meteorologists analysing the same satellite imagery were saying category 3 to 4. That gap was real. It was visible. Anyone watching could see the numbers disagree. But look at what that gap actually demonstrates. It is a sampling problem, not a suppression problem, and the evidence is in the disagreement itself. The Dvorak technique is publicly documented and openly taught. Multiple independent agencies, the Joint Typhoon Warning Center, the Japan Meteorological Agency and others, analyze the same imagery and publish estimates that routinely differ from one another, sometimes by a full category, in public every day for anyone to compare. That is the opposite of concealment. A coordinated effort to hide a storm's intensity would be the one scenario in which all the numbers agreed. Advisories update on a fixed schedule, a storm that reorganizes in 5 hours will outrun any fixed schedule, and the technique used to estimate its intensity, as we established, systematically underestimates exactly this kind of pinhole ice storm. The gap is the predictable output of a known limitation, published openly by people who write papers about the limitation. The third claim is that records are being invented to fit a narrative. That one collapses on contact with the record book. The recognized world record for intensification was set in 1983. The lowest sea level pressure ever measured was recorded in 1979. Both of those still stand. Nobody replaced them with something more convenient. If the goal were to manufacture a narrative of ever-escalating storms, leaving the two headline records with storms from the late 1970s and early 1980s would be a strange way to go about it. And here is the part I find genuinely interesting, because there is an uncomfortable middle ground that neither side of this argument tends to want. Humans are influencing these storms. That is not a fringe claim, it is the peer-reviewed one. Not by steering them, not by building them, and not by hiding them, by warming the water they run on, which raises the ceiling on how strong they can get and appears, in the observational record, to be increasing how fast they strengthen. That is the boring version. It is also the consequential one. The weather control story imagines a hidden hand with a machine. The measured reality is more unsettling, because there is no hand and no machine and no one at the controls. There is just a very large amount of extra heat in the ocean, and storms that are better at finding it. And notice where that leaves the advisory gap those claims attach to. It is not evidence of a cover-up. It is the same forecasting limitation this entire video has been about, seen from a different angle by people who reached for a different explanation. Part 16. Thursday. The public forecast calls for Dolphin to peak near 170 miles per hour of sustained wind late on Thursday, July 30th, as it passes roughly 230 miles southwest of Wake Island. That is the moment this all resolves into something, and it is close enough now to be worth stating exactly what the two outcomes look like. If the eye holds, if no outer ring organizes, if no dry air finds the core, if the storm keeps standing straight up over the deepest warm water on the planet, then Dolphin runs to something near the top of the satellite intensity scale, and we will have watched one of the more extreme intensification sequences of the modern satellite era, from beginning to end, live, with nobody able to measure it. If the eye does not hold, we will see a second ring appear on the imagery. The pinhole will go fuzzy and then broad. The peak wind will come off by 20 or 30 knots, and the storm will emerge larger, softer at the centre, and considerably harder to characterize. The record conversation will end without an answer. Beyond Thursday, the picture gets vaguer in an honest way. Guidance keeps the storm over open water well into early August, and some model solutions suggest a turn toward Japan at some point in that window. I want to be careful about that, because a track suggestion at 7 to 10 days is not a forecast in any meaningful sense. Track errors at that range are enormous. It is worth watching, and it is not worth planning around, and anyone presenting it as a coming impact is telling you something the science does not support. But step back from dolphin for a moment, because the reason this storm is worth 2 hours is not dolphin. Over 4 decades, our ability to say where a tropical cyclone will go has improved enormously. A genuine triumph of modelling, satellites, and computing, and one that has saved more lives than almost any other advance in the atmospheric sciences. Over those same 4 decades, our ability to say how strong it will be when it gets there has improved far less, and the place that failure concentrates is not the average case, it is this case, the fast one. Right now, that failure is a scientific curiosity, because dolphin is 1,000 miles from anything and the ocean does not care how strong it gets. Change one variable, put the same storm 200 miles off a populated coastline, with the same 5-hour transformation, and the failure stops being interesting and starts being a body count. Because evacuations are not planned against the storm, they are planned against yesterday's forecast of the storm. Buses are staged, hospitals are emptied, highways are reversed, and all of it is scheduled around a number that was issued before the storm decided what it was going to become. A storm that gains 60 knots overnight does not just exceed the forecast, it invalidates the plan built on it. There is a version of this problem that has already happened, more than once, and it is why intensity forecasting gets research funding at all. A storm that is a moderate hurricane at the moment the evacuation decision has to be made, and a major hurricane by the time it arrives, produces exactly the scenario emergency managers dread. People who made a reasonable decision to stay based on accurate information and then found themselves inside a storm 2 categories stronger than the one they had prepared for. The information was not wrong when it was issued. It was simply overtaken. That is what a rapid intensification event does to a warning system. It does not defeat it with bad science. It defeats it with time, and then widen the frame one more step, because this is the part that stays with me. The theoretical ceiling on a storm intensity is set by the temperature of the water. That water recorded its warmest month in history 6 weeks ago. The subsurface reservoir feeding this particular basin is carrying an anomaly described as possibly the strongest on record, and the peer-reviewed work on intensification rates finds increases that natural variability does not comfortably explain. The ocean is the largest heat reservoir this planet has. It absorbs the overwhelming majority of the extra energy the climate system retains, and it does so slowly over decades, holding that heat in a volume of water so vast that its temperature barely registers the change. Then it gives some of it back, not evenly and not gently. A tropical cyclone is one of the few mechanisms in nature capable of taking heat that has been accumulating in the ocean for years and moving it upward and outward on a timescale of days. These storms are how the planet exhales, go further out and the scale keeps expanding. The heat currently sitting in the Western Pacific warm pool did not arrive there this summer. Some of it has been accumulating for decades, pushed down beneath the surface by trade winds, stored in a volume of water that takes years to turn over. What an El Niño does is bring a portion of that stored heat back into contact with the atmosphere, and what a typhoon does is grab a piece of it and throw it into the upper troposphere in a matter of hours. The storm is the fastest moving part of a system, whose other parts move on timescales of years, decades, and centuries. It is the visible, violent tip of an enormously slow process, and go further still past the human timescale entirely, and hurricanes stop looking like disasters and start looking like plumbing. The tropics receive far more energy from the sun than they radiate away, and the poles radiate away far more than they receive. Something has to move the surplus continuously, or the planet's temperature gradient would run away from itself. Ocean currents do most of that work. The atmosphere does the rest, mostly through mid-latitude weather systems, and, at the extreme end, through tropical cyclones, which take heat out of the tropical ocean and carry it poleward in the most concentrated way the planet has available. These storms are not an aberration in the climate system. They are one of its transfer mechanisms, and we are currently adjusting the amount of heat that mechanism has to move. We have always believed that the frightening number in a hurricane is where it makes landfall, the city in the cone, the coastline in the path, the place the eye crosses. But what if the number that actually mattered was never the place at all? What if it was always the rate? Forest's record has stood for 43 years, and not because storms stopped trying to break it. It has stood because the exact combination that Forest found, The deep warm water, the perfect symmetry, the absent shear, the contracted core, all of it arriving at once and holding for a full day, is rare. What is changing is not the physics. The angular momentum argument is the same as it was in 1983. What is changing is how often the combination is available. For most of the history of these storms, the limiting factor on how fast one could strengthen was the ocean, how much warm water there was, how deep it went, how quickly the storm could exhaust it. That is the break that has failed in this basin, in this season, over this anomaly. Which means that for a storm like Dolphin, sitting where it is sitting, the ocean may no longer be the limit. The only thing left to limit it may be the storm itself, its own fragile, contracted, self-destructing core. So on Thursday, Dolphin either holds that pinhole eye or it does not. That is the whole question, and it is not a rhetorical one. It has an answer, and the answer arrives in about 48 hours. But here is the part that keeps this from being satisfying. Whichever way it goes, nobody watching this week will find out whether we just witnessed a record-class intensification. That will be settled in a reanalysis document, published a year or more from now, by analysts reconstructing a storm from an archive, long after Dolphin has come apart over cold water and stopped existing entirely.